All right, we can get started, I guess. This session is about security, stability, and scalability. We've worked a lot. We've worked very closely with our customers, that's you, for a long period of time now, and these topics keep coming up time and again. And we most recently hit upon a lot of emerging technologies, and we've incorporated them into our solutions. And we have a lot of things to share with you in that regard. And we thought, let's break it down into these three buckets and see, if there's any questions or if we can open up more dialogue, especially around how we've gone about designing our solutions, our design philosophies on the new platform, what we call our supply chain operating network, and see where it's headed in general. So maybe we can dive a little deeper. It's going to be a little technical, but we'll try to keep it at a level where it makes business sense as well. So let's move to the first slide. My name is Arun Samuga. I lead the research and development team at Elamica. This is my colleague, Antonio. We work together in the Atlanta office. This is what our 2.0 system kind of looks like. It's one view, obviously a very dirty view. It's bottom-up, built from the ground up, completely using cloud technologies. Our solution is totally based in Europe. It's currently hosted in Dublin across 3 different data centers. If you look at, it's called Availability Zone 1, Zone 2, and Zone 3. And all the different components are distributed. They are highly scalable. They are built out as services from the bottom up. The QuickLink portal solution is an entry point for a user who wants to log in, while the QuickLink solution has the B2B integration capabilities in there. So there is connectivity from a messaging perspective, as well as users can log in and access the system. So there's 2 key entry points into the system, and that's important from to know from a security standpoint. One last piece here, I think we briefly touched upon it. Everything is service-based, and there is auto-scaling enabled. We also use best-of-breed technologies in order to ensure that we take key components of what makes sense from Amazon Web Services. We take those, and then we build our stuff on top of that, and then we integrate the two in order to ensure that we are able to translate it to the most benefit for our customers. So that's a very high-level overview of what our solution kind of looks like. If we go to the next slide, I think, Antonio, you have it. So we're going to dive a little deeper into security, stability, and scalability. I'll let Antonio go into the details, and I'll provide some background on what we are seeing in the world of our existing systems, which we call 1.0, and how we are going to tackle some of those problems in the new system, which we're going to refer to as 2.0.
Thanks, Arun. So we're going to start by talking about user access to all aspects of the system. We've got some pretty fine-grained abilities to allow different people to access different parts, but we also have to start at the very beginning, which is authentication. How do you get into the system? How do you prove that you are who you are? And what we've implemented on that front is called multi-factor authentication. It's something that I think in the last 5 years has gone from being the domain of extremely secure systems to being a lot more common. We've seen a lot of data breaches take place over the last 5 years, and it's been one of those things where we've slowly had to upgrade everyone's approach to security. Multi-factor authentication is about changing how you prove who you are from just having a thing that you know, which is your password, to having both a thing that you know and a thing that you physically possess. Typically, that's your phone. In the past, it's also sometimes been a secure token, and it's also used in banking in Europe a lot, in the US less so. So we've implemented this using a third-party service called Authy that provides a lot of the glue behind the scenes to generate secure tokens and to validate those secure tokens. From our perspective, you go to log into the system, you have to provide this additional token, which you can typically get on your phone, and then that proves that you are indeed who you say you are. The other thing to note about this is that it happens without requiring an external internet connection. So if your phone can't get Wi-Fi, or you don't have access for your phone to get to the internet, you can still get these secure tokens as they're generated in a completely disconnected manner. Multi-factor authentication also extends to connectivity. So how clients connect to Elamica to actually send messages. And the way that we implement this is we have actually a patented approach that has three pieces of information for the client to provide us. One of them is the URL at which the client connects. The URL has traditionally been a single URL. Everyone connects to the same place. You provide a username and password, and that's how the system determines who you are. In the QuickLink 2.0 system, you actually have a client-specific URL that you connect to. In addition to that, you have a username and password or a certificate-based authentication, depending on which approach you choose. And then the third piece of information is we actually apply an IP filter to who can actually connect to that URL in terms of a physical location. So that provides that second factor, which is the thing you possess. The thing you possess in this case is the IP address, which corresponds to an actual machine.
And just to add one point there, when we receive data from a trading partner, we know exactly where it's coming from, because if I have allocated a specific URL to you, I'm expecting only you to come from that URL. So in general, I know it's you who's trying to come in. But on top of that, we use the certificate to actually verify that it is you. So that makes it doubly secure, if not more.
The third component of security is what we do about the data. And the best practice here has very quickly become securing data not only when it's moving around, but also once it's actually stored, making sure that just having access to the physical place where it's stored is not enough to be able to access the data itself. To that end, we use AES-256 encryption on the data when it's sitting in storage. And then once it's actually pulled out and starts being processed live, it's either processed inside a secured system or it's transferred over secure links. So it's secure at all times.
Yeah, I think another thing to note here is, I think we mentioned it briefly. So our data is currently hosted in Dublin. It's one of the Amazon regions. So Amazon has about 6 or 7 different regions throughout the world. So we are currently also looking at trying to host our data in Frankfurt, which is probably the newest of the data centers, especially in Europe, it's the newest. And they do have a few interesting characteristics in there where, you know, they have an upgraded version of what currently exists in Dublin. So we have to make a few changes in order to get there. But our eventual goal is to be able to say, we have all our data across 3 different availability zones, which is 3 different data centers in Dublin, but we might as well take it and move it to Frankfurt. And one of the things that we constantly discuss amongst our team members is, you know, one fine day we should just flip the switch and run from Frankfurt. And a few days later we run from Dublin. And if somebody says, where are you exactly running today? You should be able to say, it really doesn't matter. So that's like a vision, it's a dream. But having said that, I think the cloud technologies, especially provided by Amazon, can make it a reality if we need to go down that path.
Yeah, one of the end goals there, I think, is you end up in a place where any machine can fail at any time and something else just picks up the pieces and continues working as if nothing happened at all. And we'll talk about that some more in some of the next slides. The last component is, okay, everything is secured, but you also have to control access to the actual tokens that allow you to open the secured data. So to that end, all of our access to our infrastructure is controlled by keys. These keys are generally tightly controlled. A single key corresponds to a single person, so you know whenever someone is dealing with data, you know who it was that dealt with the data. And the different keys don't all have the same access. So certain keys will grant read-write access, certain keys will grant read access, certain keys will only grant access to certain parts of the system. All of that is controlled by our DevOps team, and they essentially are able to delegate and to know who they've delegated these different levels of access to.
I think one interesting thing to mention there, Anton, is also, I mean, what exactly is DevOps? I think people may have heard it before, but it might be worthwhile kind of defining it.
Yeah, so for a very long time, I think the operations and development sides of companies lived very much apart, and I mean operations in the technical sense. You had people who ran the servers, IT, and then you had the people who developed stuff to actually run on the servers. And they kind of lived separately. They had relatively minimal interfaces between them. DevOps is about reimagining a lot of that and reimagining almost the IT operations side as also a development side of sorts. And the reason that we have to do that is, as we'll talk about in a minute, a lot of what actually runs in the cloud has to be programmed. You have to define how a particular environment is going to look for it to be able to come up quickly and for the system to be able to react to changes in load and what have you. DevOps is the side of the house that manages all of that automatic scaling, that defines it in a reproducible way and makes it so that the infrastructure isn't a physical thing, but rather a conceptualization of what the infrastructure will be that can then be executed by the cloud environment.
Yep. So actually, let's pause there because we don't have too much material, but we want to keep it interactive. So there's 3 topics. There's security, stability, and scalability. We just highlighted some aspects of the security of our system. So maybe we can pause there and see if there's any questions on those lines. If not, we can move on. Yep.
Have you ever encountered any attacks on your system?
I'm sorry?
Have you ever encountered any attacks on your system?
Not that I do believe there were a couple of rogue hits, but this was like a year ago, and we tracked it down. There were like I think about 20 or 30,000 requests that came in over a weekend of sorts, if I'm not mistaken. But then the system, Amazon itself took care of it for us. So we really didn't have to bother because Amazon has intrusion detection systems in place. So they know if there is an attack. They look out for patterns. So they provide a good level of filter to us. And for us, especially, we have something called a high availability proxy system in place. So that sits in front of our region, which is again a representation of 3 data centers or availability zones. So in case there is a large hit in any one particular area, we're able to kind of shuffle traffic over pretty effectively. So we have 2 or 3 different layers of protection, if I may. All right.
Cool. Yeah. So let's talk about stability. The first component of stability from our perspective is how can we make sure that we don't lose data? So when you connect to the Alemica system and you send us a message, we want to make sure that if we tell you that we've received the message, we've not only received it, but we've stored it in a way that we will always be able to get to it. So even if there are issues in the processing backend, no matter what happens, if you complete your connection to us and you complete your message transmission to us, we know for a fact that it is sitting in those data centers that we were talking about, again, secured as we were talking about, and that we can get to it later on and reprocess or do whatever we need to do. If the system is running fine, obviously, this is the way that it's always worked. But the key component here is that even if the rest of the system is having issues, as long as your connection is completed successfully, you know that we have the data and we can always get to it.
Yeah, and I think one of the key things here is if you look at the trends over the past 8 to 10 years, these systems are relatively old. Some of the technologies are relatively old as well. And based on the design from the past, one of the things that was always there was a lot of importance given to connectivity. And that's because without establishing a connection, you really can't transmit data. But then people wanted to actually get acknowledgement saying, hey, I sent my message. Did you get it? So they implemented a process called an acknowledgement process. So not only were people not satisfied with the basic HTTP handshake, also known as 200 in a code form, but they also wanted to get acknowledgements back. Now, if the system is under distress, a lot of these old systems, the connectivity was not really decoupled from the message processing to begin with. So if there was an issue with message processing for some reason, maybe it's load, maybe there was an unusually large document that ate up a lot of processing power, connectivity got impacted. So trading partners would sometimes get a 200 OK and they would say, fine, I think Alemica got it. And in some cases, they didn't even check. They just assumed as long as I posted, Alemica has it. And in some cases, trading partners would actually expect a receipt acknowledgement back, tie the transmission on their systems, and look for potential issues there. So there's different levels of maturity that we see our trading partners having, especially with our current 1.0 system. So this approach fundamentally defies all of those, or it basically says, if you send us a message, you will not get an acknowledgement unless we have seen the raw message. So which means that we will almost always have it. So there is no message that can ever be lost. So I think that is huge, because when you're talking about guaranteed delivery, the first thing you're most interested is in the guarantee itself. And we actually use a store first approach in order to guarantee that the message that you sent to us has been acknowledged, but it's been acknowledged only after we've persisted the source. So this is pretty large. It took quite a bit of development effort on our side. We recently polished it and it's all in production, but I thought that was a very interesting milestone.
Yeah, and of note, there is still the concept of a receipt acknowledgement message. The difference is that now when you get a 200 OK from our connectivity solution, you know we have it. When you get a receipt acknowledgement, you know we're processing it. So we now have the ability to kind of distinguish between the two, but always, if we say something, a particular phase is OK, it's 100% OK. Part 2 is Qbased processing. This kind of ties back to store first approach in the sense that stability and high availability in general are about really breaking down every step of processing, or in this case of message processing, but of any system, and making them completely independent of one another. That way you can basically ensure that once any given system is done with its task, it can move on to the next one. You can bring up and bring down various services as needed to deploy, to do maintenance, to do whatever. The queue-based processing is what sits between all of these services. And essentially, when one service is done with it, it forks it over to the next service by putting it on a queue. That queue ensures that we then process all of the next phase in a first-in, first-out way. So the queues basically underlie the communications infrastructure internally of the entire system, just like HTTPS, SFTP, and all of those underlie the communications infrastructure with external systems. Our queues are essentially the equivalent of that.
Yeah, and I think two other points to mention there. I think queues basically act as a buffer. So if you send me something and I want to process it, and I want to throw some services at it in order to either transform it or add value to it, enrich it, and so on, then I'm better off actually, as soon as I get a request from you, I put it in a queue, and then I pull it out of the queue. So the next service can actually pull it out of your queue. So what you've effectively done is you've created a buffer. And this buffer allows you in situations where the system could be under distress. So in such cases, you can actually distribute your processing, your storage, your buffering solution can actually queue things up, which is okay because your goal is stability over speed at any point in time. Speed is very important, but stability is actually more important than speed. And that's our observation based on our relationship with our trading partners and customers. So we've deployed our queue-based processing across various service handoff points. And another thing queue-based processing allows you to do is first-in, first-out processing. So queues, again, treat them as glorified file folder systems, but they enforce first-in, first-out processing. So you know that you can never receive an order change message without receiving an order create message as long as they've been sent in the right order by the originating partner. Yeah.
Cool. So the next step is multi-channel data handling. Multi-channel data handling, actually, if you want to talk about how it used to work, basically.
Right.
Yeah.
So some of the patterns we also noticed is, over the past few years, there's been a lot of increased demand in saying, these are my logistics transactions. They have to be processed really fast because they need to have a turnaround time of 2 hours. And then these are my product movement reports, and they are humongous. They could be between 5 megabytes in size to all the way to like 50 MB in size. So we cannot employ a single service-based approach for these two problems, which are, you can call them exceptions, but they are actually needed for the business to occur successfully. But they fall into a different category because they're not 80 to 90% of the regular flow. They are 10 to 20% of the flow, which is high value, but they need to be treated separately. So what we can do currently is with a combination of the store-first approach and queue-based processing, say we take those two situations, we get a large message. So as soon as using our store-first approach, we store it. We store the raw content, but we also determine the size of the message, and we say, okay, this is a really, really large message. Let us actually send it to a separate queue for processing. So we've dedicated queue-based infrastructure and services in order to say, let's route this large document through a different path altogether. So that's one of the channels that we use for data handling. Similarly, if there's a logistics transaction that needs to be delivered within 2 hours. Now, sometimes just because of the processing state that the system is in, you might not be able to process a document within 2 hours. But at least if you have a predefined path and you have checkpoints and say, if we receive it at X, and it did not come out of this checkpoint at X plus 2 minutes, then raise an alert. So at least people are involved, people involved know about it, and you can proactively notify your trading partner that, look, there are some delays because of which this particular message, which had an SLA of 2 minutes, is actually running a little late, which is probably better than us sitting there not knowing about the problem and then realizing that that file was transferred like 20 hours later. Meanwhile, the shipper has automatically identified another carrier while the original carrier based on the contract is still waiting. So from a business perspective, you do see such patterns, and we wanted to get ahead of it with our new platform, and we put a lot of thought into how to make it more stable from some of these exception-based processing requirements that we currently see.
Yeah, from an infrastructure perspective, what this translates to is we were talking about defining how the infrastructure is assembled. We can define specific roles for pieces of the infrastructure. For example, if we're processing larger messages, we can use larger systems, larger machines, larger virtual machines to process those. And we can define those per queue, we can define them per type of data, and just spin them up only when we need them. And as soon as they get spun up, they're dedicated to that task and nothing else. So we can continue processing those while still processing normal traffic the normal way without disrupting anything.
Yeah.
Part 4 is decoupled connectivity and data transformation. We kind of talked about this a little bit when we talked about store first. What this basically means is our connectivity solution, the thing that you connect to transmit a message to us, is completely separate from the part that does actual message transformation. It doesn't, the only way that they know about each other is through these queues. So what this means is if we suddenly get a flood of messages and we don't know if they're malicious, for example, it's an attack, we can scale up our connectivity solution while we look into the problem so that nobody is affected by this sudden flood of traffic, and it doesn't affect our message processing until we make sure that all of those messages are valid. That's just one example. In general, it means that these components can be scaled separately, they can be built separately, they're maintained separately, they can be deployed separately. All of these kind of separations let us manage each component individually and let us do things like deploy fixes to one piece of the system without having to suspend all of the rest of the system. Since our connectivity solution is kind of the most important part, because as we've said, once we guarantee that once we've received a message, we're going to process it, the connectivity solution is matured very quickly. We don't make a lot of changes to it. So that means that we can deploy it a lot less frequently so that you can always rely on the fact that if you try to send us something, we'll be there to receive it. On the flip side, the message transformation aspect updates a lot more frequently. There's changes that happen for clients, et cetera, et cetera. So we can deploy that without affecting the connectivity endpoint.
And if you look at most managed file transfer tools, which is, that's where most of the SFTP, FTP, and HTTP-based protocols, protocol-based products are in the market, they actually don't have it. They don't design it this way. That's because, first of all, it takes more to build something like this, and secondly, obviously, it's more complex, and secondly, it needs more infrastructure in order to kind of deploy two different components, yet make them talk as though they're pretty seamless. So it's complex, and it's generally not available in most products in the marketplace. So we went ahead, took the extra step in order to truly decouple it. But the beauty of the solution is that when you're trying to actually onboard a partner, they are in one place. There's an overlay that actually links the two. So from a user's perspective, when they set up a partner, when they connect a partner, and when they enable data transformation for a partner, it's all happening in one place, but internally they are decoupled from each other.
I think that's all for stability. So
yeah,
if there are any
let's pause
questions
here.
on that, yeah.
Stability questions?
Yes. How do you measure the stability of the system?
There are, well, that's a good question. In some cases, there are SLAs. So we do know as of now that on an average, if we take a 20 kilobyte message, which is around the average size of a message, and we should be able to process about 45 messages per second on the connectivity channel. So we're able to receive 45 messages per second at any point in time. And we are able to process about 22 messages per second. And when I say this, what I mean is this is at sustained loads. So in other words, at any point in time, if there is 22 messages per second, there is no delay. There's zero delay. But if there's more than 22 messages per second that come and hit us, then it will start getting queued. But having said that, the queues also kind of drain out very, very quickly, depending on how fast the services free up. So those are our benchmarks. So for large documents, we do have separate benchmarks, and we're going to publish that soon. But I think we left it at a place where we said, if it is 15 MB, then we need to be able to process it within 1 minute. So those are some of the key things that we use in order to actually track and see if we are falling behind or not. And the second part is, as and when we deploy, so there's two pieces of, there's two aspects that makes the system dynamic. So the first aspect is the mapping, that's the data transformation, you're adding more partners and so on. So there's that part that's constantly growing. And the second part is there are special functions that are needed. So if a customer needs to split a large message by line item and then deliver it to the end partner, or I get a copy of a message, I massage some data in it, send it to 2 different partners with 2 different pieces of information, or I route that document to a portal type application for visibility. So there are different patterns. Now, all that is handled through services. So there are 2 types of changes that are going into the system at any point in time that makes it dynamic. And every time we publish any of these changes, there is a series of regression tests that we run. And we also run a series of performance tests, which is part of our hardness that we have built out. So any deviation from that, from a design time, code publication perspective, we catch it. But in runtime, we follow these metrics in order to ensure that the system is healthy and it's as stable as it was when we designed it.
Also worth mentioning, at runtime, we have monitoring of all of the systems that we run, and we have alerting hooked up to that monitoring. We'll talk about this in the next section a little bit, but those same alerts are also hooked into auto-scaling mechanisms, so that if things seem to be slowing down, if we're using too much CPU while processing messages or whatever, we can kick in and add additional capacity to deal with that.
But that's a good point, though, because we're going to cover it in scalability. But Michael, to answer your question around, we have metrics internally to track it. I guess that's the first answer. But the second answer is, if we observe some patterns, then we are able to make changes very, very quickly. We really don't have to wait to procure infrastructure, sign off a contract. We don't have to do any of that. In fact, it's all code. We actually go ahead and tweak the parameters, run the code, and you have another instance. In some cases, we can actually automatically deploy these based on certain critical thresholds. So if your CPU consistently hits 64% at 5 p.m. on a particular day, boom, create a new instance, run it there, and shut it down. We can do things like that as well. So there are different aspects of handling stability issues in general. But I think the key point is we know what our stability boundaries are at this point, limits are rather, and we constantly monitor those.
I have 2 questions. First question, obviously you can process a lot of messages in real time without them landing in the wait queue. However, do you know what is the average time the message spends in the queue? For the ones that don't get processed with real time. I know it's maybe like that.
It's milliseconds basically. In simple words, it's milliseconds. However, I think one aspect we need to keep in mind is it's totally based on how many messages came in at a particular time. So if we, I think we also did tests for sustained 25,000 messages. We tried to submit 25,000 messages in one go, and I think it drained out. So on an average, actually I have a better number for you. On an average, in a given 10-hour day, we are able to process about 2 million messages easily, without any issues. So it will drain out. So I know it's not the exact answer you're looking for, but because there is no exact answer to your question. It's completely dependent on how many messages came in, how many messages are being processed, how many are in the backlog, and so on. So a better way to look at it is to say, with sustained loads, and if you give it about 10 hours, how many messages can you actually process, including the wait time in the queues, pull, push, NQ, DQ, etc. So it's about 2 million per day in a 10-hour day.
And I think the processing of the message depends on the message size, maybe, or message, I don't know, type, whatever.
Yeah.
The processing itself shouldn't take long.
No. Processing typically, again, is in milliseconds. And when you say processing, one of the things that we do is, earlier what we did was there was a lot of point-to-point type connections. So in many cases, if you sent me an EDI message, I would just pass it through to the partner and ask the partner to make the changes in their system to transform it. That's one such pattern. The second pattern was, you send me an EDI, but I can only accept an SAP IDOC. So Elemica just transformed it directly from EDI to IDOC. With the new platform, what we're doing is, regardless of these two situations, if you send an EDI, we first translate it to what we call a universal business document. So that's our core canonical structure, which we eventually use for correlation, extrapolation, analytics, and so on, proactive notifications, etc. So every relationship, every document transfer and processing, it has two steps now. Source to UBD, Universal Business Document, and UBD to target. And that definitely adds more processing. It's interesting you asked that, because that's a fundamental difference between the 2.0 system and the 1.0 system, or any other systems that you typically see in the market. We always translate everything through a core canonical structure. And that obviously adds more processing. But it also gives us the freedom to say, there are some things which you should always add in the source to UBD, and some things that correspond to the target system, always added from the UBD to the target side of it. So that way we also distribute processing, keep it streamlined by partner, by document type, and in some cases by a trading partner pair and document type combination. So we are able to play around with these parameters, and if you extrapolate all of this and tie it together from a scalability perspective, I think what we are effectively trying to say is, we now have a truly distributed process-based system, and we can scale any of these components at will. So if we see issues in splitting on the receiver side of the equation, UBD to the receiver, we can actually spool up some more services that only cater to that, and we can speed it up that way. So we have more options to play around with the increased parameters that we have from a processing standpoint.
Thank you. And the second question, sorry.
No, please take your time. We have about 12 more minutes.
So the second question is regarding the approach with queues.
Yeah.
On the one hand, of course, it's safe because you make sure messages are always there and can't be lost, process one after another, first in, first out. But on the other hand, isn't there a danger of, let's say, one message is stuck that is way in front of all the other messages, and it's stuck for some reason, I don't know, too big or whatever. Of course, you have a delay of all the other messages waiting. So are there any methods of you guys tracking the all these problems of the queues, and how can you react quickly to solve those and free the queue?
There are specific turnaround times that are needed, that are tracked. So if a message is not dequeued within X amount of time, depending on the message type, it automatically gets added to I hate to call it a dead letter queue, but it gets into a separate place, and it gets alerted so that people have visibility into it, and we act upon it very quickly. That's the simplest answer to your question. Of course, it totally depends on the type of the message. It depends on the time of the day. It also depends on the partner. So in some cases you want it because you really want to wait for that big message to go through before you process the others. again, stability is more important than speed. So it's an optimization exercise. There's no simple answer, but the overarching answer is if we are aware that there is a problem, then we actually move it over. We dequeue it into a transient state where we just say, take care of this separately.
It's also worth noting that while we guarantee first in, first out, that doesn't mean that we process messages serially. So even though we are on a queue and we're processing things first in, first out, there could be multiple instances consuming from one queue. And in that case, having one instance stuck on one message will not block all the other ones.
That's right.
So since all of those metrics that Arun was talking about in terms of how long it's taking to dequeue things, those can also be hooked into the same scaling decisions that we're going to talk about here in a minute, and basically lead to, it's taking too long to get through the queue, add additional capacity to the system, spin up that capacity, you add additional consumers, those consumers start taking messages off the queue, and we keep things flowing that way.
All right, let's move on to scalability.
So this is something that at this point we've talked about several times, but the core aspect of our scalability is this ability to automatically provision environments, and within those environments automatically provision specific instances and deploy specific parts of the system. So this means that if we're dealing with a particularly large number of messages at a particular time of day, we can either react to it as soon as we notice that our processing is slowing down, or if it's scheduled stuff, we can go ahead and schedule an increase in capacity. So we know that at 5 p.m. every day, we're going to start processing more messages than usual. At 4:55, we can start spinning up the additional capacity, so it's exactly available for peak load. And then as soon as we know that that peak load is going to end, we can scale it all back down. So it lets us really be able to move the code that underlies all of the processing wherever we need it to.
And I think one interesting point there, we use cloud formation templates that's provided by Amazon. One interesting story there, we wanted to move our data center, which was originally in Oregon in the US, to Dublin in Ireland. And it took us about 4 hours of downtime because it was the first time we were doing it. But the fact that we had everything templatized, the actual time for the system to execute and come up was about 40 minutes. The remaining time was us ensuring the data was okay and all that. But just because of the cloud formation templates, we were able to completely replicate a totally new instance, a totally new environment of our existing version in about 40 minutes. So it's that powerful.
Again, we've talked about this a bit, but based on utilization, being able to deploy these environments, bring them up, bring them down, and all of this is hooked into, I think this is actually 3, so all of this is hooked into these alarms. We monitor a lot of metrics, a lot of technical metrics, CPU usage, memory usage, queue depth, all of these things are indicators, and they feed into automatic decisions to scale up, scale down.
I think one more point there was when we talk about increasing or decreasing utilization. We recently were approached, I think by two companies that came and asked us, if we came to you and said we want to do some testing and we're going to stop that testing in a month, can you help us do this? And we said, yes, that's exactly why we have cloud-based solutions. So we have on-demand instances, we have reserved instances. In those cases where we know that the demand is pretty consistent, we go with reserved instances because they're definitely much cheaper in the long run. But on-demand instances are also available. So if you as a customer come to us and say, I have this project, I want to test it out, but I also want to do a performance test, and it's going to last 3 days. So we can say, yeah, sure. Here is an environment that we completely brought up only for you. There's nobody else who is also on that system, either on that system. So we just bring it up for you. You do your testing using that, and it's called cloud bursting in the technical world. But we can do cloud bursting for you. You use our systems on demand, and as soon as you're done, we bring it down. So we've just paid for the difference. We've paid for the usage, as opposed to, you know, what traditionally happens where you procure hardware, get a virtual machine, install it, and so on and so forth. So that fundamentally reduces the cycle time associated with, you know, it's all about being agile and trying to make changes as quickly as possible, trying to get to the results you need to get to as soon as possible, and moving on, and infrastructure does not need to come in the way.
And of course, all of these alarms that are hooked up to automated systems also notify actual human beings so that if something anomalous is happening, we're aware of that as soon as it starts happening. So they basically serve two purposes in that sense. They let us make sure to stay ahead of surges in traffic, but they also let us be aware of surges in traffic. So if it's something that we're not expecting, we can double check and say, wait, is this normal traffic? Is it some sort of issue on a customer system that's causing floods, or is it something that, like, we're having trouble keeping up? Is it something where we're seeing some sort of attack happening? So we can kind of react to those as human beings while continuing to maintain our performance, because the system is also automatically reacting to all of those changes. And then the fourth part is distributing traffic across these instances. So the queue is the core mechanism in which we do that. When we have a particular service and there are 7 instances available to run that service, the service before it puts all of their output onto a queue. We have instances that can then pick stuff off of the queue as their capacity becomes available, and then when they're done with it, they move it on to the next phase of processing. So we can essentially distribute the traffic via these queues in an even way when everyone is running the same way, or an uneven way in cases where certain messages are taking longer to process, or certain issues are happening on one particular instance that's causing it to run slower than others.
Yeah, I mean, if Covestra wants their own instance, then so be it, you know.
Yeah, so there's actually, so we kind of talked about this on the previous slide, but
Susanna, if you want your own instance, you get one.
Well, there's personalities to these instances that we can set up, essentially, where we can say this instance is reserved for processing messages from this company, or this instance is reserved for processing large messages, or in certain cases what we can do is we have these regression tests that Arun was talking about, and when we get ready to deploy a new release to the system, we can actually deploy it to one particular instance in production, run all of our regression tests, make sure that we haven't broken anything, and only then do we trigger the deploy. So that lets us be sure that when we actually push code, it's not going to break any of what's already there, and we're going to continue processing messages the way that we usually process them.
And then we can tie it back to the performance numbers again to see for any deviation. So that's how we maintain the health of the system as we go along. It's only going to get more complex and bigger, but if we have these nuts and bolts built out early on, and we are able to replicate them at will on demand, then we have a more deterministic system in the long run. And all this is possible because we are completely cloud-based, and Amazon provides us with a great service. Questions? Yeah, so Sergey, I don't think you heard it right. So Susanna is basically, and correct me if I'm wrong, there's going to be requirements for multiple data sources eventually. Data streaming, there's going to be Internet of Things and so on. Are we saying at this point that we have unlimited scalability, or do we have constraints? I think that's... Well, no, I would not say there are no constraints, because currently we've managed to get it to a state where we can easily handle 2 times to 10 times the existing messaging traffic of our 1.0 system, because we need to have a baseline. any system design, there's a common, I keep saying this a lot of times, you can get to 80% of your goals effectively, 60% of your goals very fast. Getting from 80 to 90 takes time, and 90 to 100 might be very expensive. It might not be worth it. So you need to draw a boundary somewhere. And what we did was we said between 2 to 10 times the volume of the current system with the following SLAs, which I briefly mentioned, around 22 messages per second for transformation and 44, I think, for connectivity. As long as we do that consistently, and that we achieve with 6 service fabric nodes and 2 scribe nodes, which is our data facade node. So we are able to do all of this with that pattern. Now, if we realize that there's going to be more requirements, then we will actually need to investigate. We need to put in some more time to see if the current infrastructure is good enough, or do we need to scale it even further. So to answer your question, no, it's not unlimited scalability. It has its constraints. But I think we've designed it to a point where the problem we're trying to solve is not constrained at all.
And I think we've also added levers that we can pull.
Yeah.
So if something is going slow, we no longer have to go and fix how fast the processing is going. We can also just scale it up while we deal with the performance issues that are happening inherently in the code. So it's just additional levers that we can pull to deal with the problem.
We have about 20 seconds.
I think we're actually counting up now. I think we're 20
okay,
seconds
sorry.
past at this point.
Sorry. All right. Thanks a lot for your time, and hopefully it was informative enough. Thanks.